Hello everyone, in this tutorial you're gonna become familiar with a type of force that can create a torsion and bending. As you can see here, we have a very simple profile with a height of 400 millimeter and 600 millimeter length, and we have 800 Newton force applied in the Z direction, and this force will create a torsion and also bending at a pinpoint in that area. So before starting to simulate this in Abacus, I want to first show you the hand calculation that we have. So what we have here as a torque can be calculated by force times the length. So what we have here, 800 times the length, that will give us 48,000 times 10 power 4 Newton millimeter. And also for bending, same, force times length, and here the length is 400, so we find the bending moment. And using a torsion and torque and bending moment, we can calculate the maximum principal stress using this formula. And again, these are a basic engineering formula that you become familiar in the first year of engineering course at university. So maximum principal stress is 71.4 megapascal, and minimum principal stress is minus 20.44 megapascal. And maximum torsional stress can be calculated from this formula. That value is 38.21 megapascal. So now let's simulate this one in Abacus to see what we're gonna get and how close is our numerical result to a hand calculation. Right, okay, let's now create our geometry in Abacus. So I'm going to right click on this, create, and I'm going to do 3D deformable solid, this time sweep. We're not going to use extrusion anymore. And for approximate guide size, let's skip this 1000, because if you look at our part size, you'll see that we have 400 and 600, so 1000 will be a good guide for us. So click on continue, and so I'm going to draw one line from here and another line here, then use a dimension. From here to here is 400, and from here to here is 600. And then I'm going to create a fillet in this corner to get rid of the singularity point. So let's just use this one, create a fillet between the two curves, and select okay, so the radius is going to be 40. And now we have to select two lines, so I'm going to select this one and this one. So that's basically our fillet. We can also add a dimension back by selecting this one and this two, 600. So we're done with this, click on OK, and then now we should sketch a sweep path. Okay, and now we want it would ask us to enter a maximum scale for the section sketch. So it will ask us what you want to be the guide sketch area. Because the cross section area is quite small, I'm happy with 100, maybe 200. Okay, so as you can see, this is a 200 by 200 sketching area, and what I'm going to do, I'm going to draw this circular profile. And for a dimension, I will say the radius is 20 millimeter. So now cancel this dimension, click on OK, and as you can see, now we have this perfect like a pipe shape part. Next step is to create a property. So what I'm going to do, I'm going to add I'm going to make it out of steel, and for mechanical elasticity, elastic. And for Young modulus, let's say 210 E5. And for Young modulus, we can say 0.3. Click on OK, and I'm going to create a section for this. I'm going to call this one still homogeneous. Continue, and still we don't need to use this planar thickness because this is the one that we only use for 2D. This is already 3D and has a thickness Z direction, so avoid ticking this box. Click on continue and assign this one to the geometry and click on OK, and then OK. So as you can see, now we have this part and we have a still as assembly. The next step is to add that in assembly section, and again we have one single part I'm going to import it as a dependent mesh on a part. Click on OK, and I don't need to do anything else, as I said, because it's just a single part. The next step is to create a step, which is going to be static simulation initial. We can activate a non-linear. It's not going to really change the result for the number of the increment 1000, but again, this is going to be a quick simulation, so you don't really need that many. For initial 0.1, for minimum 15. So if you want to know more about why we chose these values, please watch the video in the principal section about step in Abacus. So click on OK, and next step is to interaction. So because I'm going to apply a force on face, and in Abacus we don't have that, what we need to do, we need to create that coupling. And in order to do that, I want to offset a point from this face. So I will select the offset from a point. So I select this one, and I'm going to offset it, let's say 20, 0 and 0. And as I mentioned, the value that I put there, 20, 30, 40, is not really affecting your result. Okay, so so don't worry about what you put there. And then what I will do, I will make this one as a reference point, and I'm going to copy this one to this face. So let's use coupling, select this one, and node region, select this face, click on OK. So I couple that one to that face, and in a load section I will fix the bottom part, and I'll select this one, click on done, and I'm going to use a pin. And for this one, I'm going to select a concentrated force, select this one, and so this one should be in a -z direction, so I'll put -800, and this one 0, and this one 0, click on OK. The next step is mesh. If I go to the part, you see that my part is in orange, and that is not a good sign, because that means that I cannot have a free structure or sweep mesh. So what I need to do, I need to create a section cut and to create a partition for my part, and I do that in a part section because my mesh is in a dependent. So I can do that using partition cell, use an end side patch, and here I'm going to say select edge, select this edge, create partition. So as you can see, I have one partition here. Now I select the top one, again select edge, and select this one, create partition. So if I go back to mesh, you'll see that the color turned yellow, so that means that I can apply a sweep mesh to this one and assign a mesh. Let's see, if I say apply, 13 is quite coarse, let's say 5, see what will happen. 5 is okay, but if you're using an educational version, maybe you can apply a little bit coarse mesh because you're limited with the number of the nodes. So assign this one, say yes. So this is the mesh. So we are done with the mesh section. The next step is to create a job, and I'm going to create a job for this one. And if I have done everything correctly, I shouldn't get any error. We will find out in a second. So let's just monitor this one to see that if it's going to get any error here. So I didn't get any error, so job is complete. Analysis input process is completed, so there's no error, and now we just need to wait for a simulation to be done. As I mentioned, this is a quick simulation, so it's done after 6 increments. So let's just see the result and say this one. Okay, so this is a what misses stress, and let's go to maximum principal, and you can see the value is 7.4 times 10. So if we add that one, that's going to be 74.28 megapascal. And if we compare that with our maximum principal state that we found from the can calculation, is quite close. I mean, especially when we have a 3D model, it's very difficult to have an absolutely perfect values like same as each other, because when your geometry become more complex, generally numerical model will give you more accurate result, but in simple cases the hand calculation is more accurate. And also we can check the shear value as well. So this is the shear value 36, and so this is basically maximum torsional shear stress, so that's 38.21. So let's see what we got here. So 36.49. So again, very close to the hand calculation. Obviously there is going to be always a difference. As I mentioned, you would never going to get the absolute exact value same as the hand calculation. In order to see the stress in a different part of the geometry, you can use this prop value, and basically either you can have them on an element, which the result comes from the average of the 8 nodes that you have there, and or you can go on a node and you can have the stress on each individual node for this model. So I hope you enjoyed this simulation and you learned a little bit about torsion and bending, and I hope to see you in the next video. Thank you so much for watching.